Welcome to A-level thermodynamics. At AS level, you mastered the macroscopic mechanics of the visible world, calculating the kinetic and potential energies of falling masses and accelerating cars. Now, we shift our focus to the hidden microscopic world. Thermodynamics is the study of how the kinetic and potential energies of invisible atoms dictate the temperature, pressure, and state of the materials you interact with every day. It is the crucial bridge between particle mechanics and the readings on your laboratory thermometer, explaining how energy enters or leaves a system as heat or work. Our first topic is internal energy. We begin by defining exactly what energy a substance holds. Internal energy is the sum of a random distribution of kinetic and potential energies associated with the molecules of a system. The Cambridge mark scheme is unforgiving here. Miss the word random and you will lose the mark. We will explore how this energy relates to temperature and why, for an ideal gas, we assume zero intermolecular forces. This means zero potential energy, making the internal energy of an ideal gas entirely kinetic.
Once you understand internal energy, you need to know how to change it. This brings us to the first law of thermodynamics. The change in internal energy equals the heat supplied to the system plus the work done on the system. The biggest discriminator between A star and B candidates is the sign convention here. If a gas expands, it pushes back and does work on its surroundings, meaning the work done on the gas is negative. You must state your signs explicitly before writing down any numbers.
Next, we link these theoretical energy transfers to observable temperature changes. Specific heat capacity tells you how much energy is required to raise the temperature of 1 kilogram of a substance by exactly 1 Kelvin, without changing its state. You will use this to calculate energy transfers and mathematically model standard laboratory experiments. Crucially, you will need to evaluate these practicals, identifying how heat lost to the surroundings skews your final calculated values, and how to mitigate those errors.
Finally, what happens when you heat a substance but its thermometer reading does not change? This brings us to specific latent heat. When a solid melts into a liquid or a liquid boils into a gas, the thermal energy supplied breaks intermolecular bonds rather than increasing molecular speed. The temperature stays completely flat. You will calculate the exact energy required to completely change the state of a specific mass and explain these phase changes strictly in terms of molecular potential energy.
Thermodynamics is a highly interconnected unit. You cannot understand the first law without understanding internal energy, and you cannot apply it to real materials without heat capacity. By the end of this unit, you will confidently define internal energy, apply the first law of thermodynamics to ideal gases, and calculate the exact thermal energy needed to heat, melt, and boil materials. You are ready to begin.